Start then. So hello everyone, and thank you for joining us tonight to learn more about nuclear energy here in Nebraska. My name is Laura Cassie. I will be hosting the event tonight. I am a conservation director serving Southeast Nebraska for the AmeriCorps Common Ground program. So the Common Ground program holds educational webinars and events about conservation issues such as water quality, clean energy, and soil health. We focus on educating the public and preserving Nebraska's natural legacy. A couple items before we start. If you have any questions during the presentation, please type those in the Q&A option at the bottom of the screen or in the chat box. We will be doing questions at the end, and then during that time, there will be a poll that will pop up on your screen and that we just ask you to please fill out. This is really important for measuring our outreach, and it's used for grant reporting purposes. Also, this event is being recorded and will be put up on the Conservation Nebraska website. Today, we are joined by Daniel Buman. He is the Director of Nuclear Oversight and Strategic Asset Management for Nebraska Public Power District's Cooper Nuclear Station. He's been with the Cooper Nuclear Station since 1987, and he's done a lot of different things while he's been there. So Dan, whenever you're ready, I can get us set up.
Okay. Thank you, Laura. I appreciate and want to thank you for the opportunity to be able to discuss about one of my favorite topics, which is Cooper Station. It's a very important asset for NPPD, and we want to be able to educate. And if there's any questions that you have, please feel free to ask, and we'll go through. Go ahead to the next slide. Cooper is one of several facilities that we have for generation of power. NPPD has a very diverse generation portfolio. We believe that this diverse generation portfolio is what's been able to maintain a very low carbon-free electricity to the state of Nebraska, as well as very reliable and affordable electricity. As you can see, it includes solar, hydro, wind, along with nuclear, and there's reasons for the diversity. It provides a very reliable and resilient area. Next slide, please. So one of the reasons of why diversity is so important is this is an actual picture taken from the average monthly load of what we've seen, what NPPD's seen within its system for the last year. And so what you're seeing there on the blue line is the load, and you see that as the load goes up, as we have to produce more electricity, we obviously have to be able to ramp up and have generation available for that. The yellow line that you're seeing there is actually wind generation, and you can see what happens here is that as the load goes up, while these are not to scale, they show you the trends that occur. When we have peaks of load where we have to have a lot of generation, many times that coincides with low wind. And then also when we have low load, and so we don't need as much, we have very much of a high wind during those time frames. So the diversification and having both in the mix, having several different areas provides us over a whole range of severe weather and various other extreme events be able to provide power. Next slide. Specifically, one of the reasons we chose nuclear, there's several different items in nuclear and why this is very important for diversity. Nuclear power plants, again, they have the highest average capacity factor of any electric source. They basically come on and they stay on, and so they're always there no matter what you have. Even when you have extreme events going through, they're very robust in their design. They can operate 24/7 for as long as 24 months nonstop. Cooper itself, when we talk of megawatts, but to give you some sort of idea what that amounts to, if you take the average energy use for any homes, CNS provides enough energy for basically 385,000 homes. Again, we'll talk a little bit more about this and give some specifics, but we can safely operate through extreme weather events. The one item that we do see is that there's a lot of trends based on energy diversity. It's being taken for granted. People expect the lights to be on. And we want to be able to provide that. But when it's being taken for granted and not always recognized in the market, sometimes that can place the energy diversity seriously at risk. Next slide. Um, so some quick facts. Cooper is an 820 megawatt boiling water reactor. As I said, if you look at the average energy usage of a home, that comes out to roughly 385,000 homes. Obviously, it goes throughout all of Nebraska and providing a large portion of the carbon-free electricity for Nebraska. It's located 3 miles south of Brownville, Nebraska. Some items that we have a oversight by the Nuclear Regulatory Commission. They have different areas where they place you, and basically they in the best column or the column 1, they have a regime of inspections that they will perform, and going over there, if your performance is not good or if they have concerns, then you would move to the other ones. We've been in the best NRC oversight column since 2012. There's also another group called INPO. It's the Institute of Nuclear Power Operations. And what they look at is they look at overall excellence of operation. And so we have been rated exemplary, or the best rating category in the industry since 2016. Again, a lot of good performance there. We receive accolades on the NRC tests security force. Obviously, we have a security force here on site. They're one of the top ranked security forces in the nation. We are the source of a lot of benchmark. People will come to see how we have that and look at what we have. But again, it's all about the people and the security force that we have here. And then we've been establishing several new records in performance. We've worked a lot on our human performance and industrial safety. We have over 1,000 days since the last injury beyond minor first aid. Again, that doesn't just happen, but that's a focus on making sure from human performance tools and making sure that we're doing the right things. We've been able to maintain that high levels of safety, as well as generation. So in 2019 and to October of 2020, we operated 679 days of safe continuous generation, and even that was all through the extreme flood that occurred in 2019 when Cooper was built. The designers built up by about 13 feet above the floodplain, so we remained completely dry. We're able to continue to operate, and we operated under that extreme event for like I said, the entire, pretty much most of the 2019. We shut down in October. We shut down once every 24 months, and we basically refuel the vessel. We take about a third of the fuel out and put in another new fuel that's in there, and then we're able to run again then for another 24 months. So in October, we shut down. We restarted, and since we've been up and going, since we restarted in November, we've been running again safe continuous operation. We're currently on 200 and some days safe operation, continuing to go, and even through the polar vortex. So again, very reliable, very dependable. Next slide. So other impacts, when we look at impacts to the state, NEI is a consulting firm out of DC. They provide a lot of input, and they're kind of a input working with the NRC, working with the industry. They do economic studies for the effect of different plants. In the last economic study that we did, Cooper's operation supports more than 1,000 Nebraska jobs, with 680 of those in the 5 neighboring counties just down in this area. So again, very major supplier for jobs. We provide more than 112 million annually in state economic output. And again, and it's 5 neighboring counties, it's 66 million in there. So again, very, very big impact, especially to the local economies around here. From an environmental impact, we typically go, because we shut down once every 2 years, we typically do our snapshots on a 2-year basis, so that 1 year where we run the entire year, it would show a much higher amounts of carbon-free energy. And then when we shut down for a month in there, that lowers it down. So we take a snapshot. So we basically, over that 2-year period, NPPD provided Nebraska customers 65% of their electricity, all carbon-free. Of that, Cooper contributed 48.6%. And you can see wind there is at 8.3, hydro is at 8%. Again, those are very, very big items, but at the output that we have of 680 megawatts, we are the biggest drivers for the carbon-free. So if we were to look at how the nuclear plant works, if we look at the fission products here, what you see is the diagram over on the left-hand side. You see they talk of a slow neutron, and so that's an overall energy rating of a neutron. It's gone through water and it slows itself on down, and what it does is it impacts into a nucleus, uranium U-235 nucleus. That excites that nucleus, and it actually causes it then to split into 2 different fission fragments, 2 different elements there. It will also provide between 2 and 3, depending upon what those fission fragments are, 2 to 3 neutrons that will go out. Those will be going very slow, or will be slowed down by the water, again, moderated. If those fast neutrons hit one of the nucleus, they go right on through. They don't, it has to be a slow neutron. It's called a moderator. But when that breaks apart, it also produces an awful lot of heat, and that heat is what we use. So next slide. That heat inside the reactor will actually cause the water to boil. So over here on the left, again on the left-hand side, you see the reactor vessel there, and you see the heat down in the bottom there, turning the water into steam. The steam goes out, goes over to the turbine, obviously turns the turbine and the generator, which then produces the electricity. The excess steam then goes down and goes into the condenser. The condenser has piping. The condenser's at a vacuum. So we also take then water out of the Missouri River, and we pump through this piping that cools down that steam and condenses it back to water. Now, as I said, the condenser is at a negative pressure. So if there's any sort of leaks or anything else, any of the river water would go out. You never get anything coming outward. It's always coming back in, but it goes into the condenser. Once it condenses, it's pumped, and then it's pumped back to the reactor vessel, where the whole cycle starts over again. So that's basically how nuclear power works, how we generate it. As far as the energy density, and one of the reasons why it's so very valuable, the reactor core is made up of a lot of what they call uranium fuel pellets. And if you were to take 5 of these pellets, they'll come up and they'll be about the size of a crayon. That's the best way of looking at it. Sometimes describe the pellets like a pencil eraser. Can you go back one slide? Can kind of be like a pencil eraser, but when you stack them together, of 5 of them, to give you an idea of the size, it looks about like a crayon. So to get some sort of idea of the amount of energy, and it's the energy density that really goes, we start, as I said, we refuel, we put in about 1/3 of the core once every 24 months. And so we will go in and it will run then and be able to run at 100% power 24/7 all the way through. So those 5 pellets, if you look at that, that's the equivalent of 15 barrels of oil, or about 150 gallons of oil, 12.5 tons of wood, 5 tons of coal, or 85,000 cubic feet of natural gas. So a lot of energy in a very small amount there. Go to the next slide. each of these fuel pellets then are put inside what's called a fuel bundle. And what you're seeing here over on the right-hand side is a cutaway of 4 different fuel bundles that are in there. The one that's cut away, you can kind of see those little rods sticking up in there. Within those rods, there's fuel pellets that go in there. And so within each one of those bundles, you see 92 fuel rods, or a total of, when you take the 548, 50,000 fuel rods in total inside the core. There are pellets that are stacked up all the way up and through there, so that we end up having almost 19 million fuel pellets inside the core. So again, a large amount of energy that's available to us, and that's what provides a lot of the advantages. So now we get into the things of the polar vortex as an example. During that time frame, we obviously had fuel in the core on site. That's why the diversity is so important to us, that we were able to keep running through that. Same thing occurred, with the flooding. We didn't need to have any sort of access for rail, for anything else of bringing in. We had sufficient fuel to be able to do that. Next slide, please. So we talked about shutting down once every 24 months, and here's some pictures. This is new fuel coming in. This just gives you an idea of the size. So when it comes in, they will be unpacking. They'll do inspections of it. They'll be doing final quality inspections. It comes having had UT very high amounts of quality control on those, but again, we look at each one, look at each pin to make sure there's nothing that's in there that there was no damage to during shipping or anything else. Next slide. Then what we do is we will disassemble the vessel, and what you're seeing here is basically the reactor head, and you can see the people in there to give you some sort of idea about what we're talking about. The bolts that are on there, they're taking, and they would unbolt that. They'll bring a crane down, they'll lift that head up, and this whole, what you're looking inside of is a cavity. And what you're going to see in the next picture here is that cavity is flooded with water, and we're looking on down through there. But for right now, yeah, so when you're looking on down now, you look in the center there where you can see the light blue. That's the area that you were looking at. They've taken the reactor head off. You're actually looking down into the core. You're looking down through about 65 feet of water. So the clarity of water and the purity of water is extremely high. The circular C-shaped sort of thing that you have that with a few people on in there, that's basically an auxiliary platform that we put in. They do that so that they can be doing testing during the refuel. They do whole lot more than refuel. We do examinations, we check, we look for different items. We're doing a lot of both visual inspections as well as ultrasonic testing, making sure that everything is as we would expect, that we're not seeing any sort of wear or having anything else, so we can always be able to detect it. At the top there, you see kind of an orange structure with something going down through the center. It's actually going underwater. That's the actual refuel bridge. That actually runs over the top of this inspection platform and goes back and forth. But that lattice that you see going on down towards the bottom is basically is an extendable crane that goes down, reaches down through all the water, gets a hold of the fuel bundle, will grab the fuel bundle. They will be looking through cameras and can look down in the water, make sure they have the right bundle. When they're sure they have the right bundle, they withdraw it out of the core. They would bring it out, and at the very bottom of the picture, you see kind of a slot. They bring it, and they maintain the bundle underneath water during the entire time frame, and that now goes off and goes over to the spent fuel pool. So they move fuel in and out through that particular path going in there. It's again, once every 24 months, and when our normal staffing is around about 625. During the outages, we will bring in anywhere between 600 to 1,000 additional people. So again, it's a lot of activity. Typically takes us about 30 days, and we do refueling, do major maintenance, and get the unit ready to go, making sure it's going to be able to run for another 24 months. Next slide. So Cooper's future. Cooper is currently licensed to operate to 2034. That's the end of our existing license. It was originally licensed for 40 years to 2014. At that particular time frame, we had gone through and had done extensive studying. And as I said, we talk about the examinations we've done to look to make sure that we're not seeing any sort of wear or anything else. And based upon that, we were granted an additional 20 years of license. There are several plants that have gone out and actually seen some additional 20 years. So being able to operate out to 80 years. And right now, EPRI is leading studies of saying that they have the potential of, because of the amount of margin and robustness they have, to be able to operate even longer. But we're currently working to maintain the asset so that we can maintain that. No decision has been made as of yet. We're looking at that, but that's a possibility. We're doing everything we can to make sure it maintains as a viable asset for potentially extending its operation beyond 2034 to 2054. To be able to do that, we've also established partnerships with schools, with colleges, to basically develop and attract new talent and make the employee pipeline. That's what is the biggest item out there to the partnership with the local schools and colleges. We hire a lot of people that come in and they want to come in, they want to work here, they've lived around in this area, and that's what they want to end up doing. So it's a very big it tends to keep instead of having a brain drain, it tends to keep people in Nebraska. We are also working with and looking at, there are new advanced reactors that are coming in. None of those have been built to date. There's several different technologies that are have a lot of advancement. They have some capabilities to be able to very rapidly load follow, which can be very viable with, especially with large penetration of wind. We're continuing to follow that. We're engaged with several different vendors that are in there. Just as so I can put in a plug, there's been a group of individuals that are having a Nebraska Advanced Nuclear Forum that's going to be on October 21st. It's going to be in Lincoln at the Southeast Community College continuing education area, looking at bringing in the vendors, different all the different technologies, be able to talk about what they have, what their abilities are, what they can bring to the table to be able to go forward. If you want to see more information, I've included the link there for you. It's at www.southeast.edu/NANF, and you'll be able to see all the information. Again, we're looking at that on October 21st. And if you're interested in any of that, I welcome you to be able to come. I'm looking forward to that particular one. Are there any questions? I think you're on mute, Laura.
Thank you. So while people are thinking of questions, I'm gonna just release a poll real quick for everybody. Very quick, it'll take you like a minute. And I just wanted to thank you, Dan, so much for doing your talk today. It's always really cool to learn more about different renewable energy here in the state. So if anybody does have any questions, just please put that in the Q&A option or in the chat below. Either one works. So I have a couple questions.
Okay.
So do you think that nuclear power can be expanded here in the state? Because I know we had the one in Elkhorn, but that has since closed. So do you think we can do it more?
Yeah. So the one it was actually up in Fort Calhoun. That has closed on down. I believe that as you look going forward, I'm a very firm believer in nuclear power. Our CEO Tom Kent has stated we are one of 21 corporations in the United States that have the capability and have the experience to be able to run a nuclear power plant. And so therefore, we believe that that's a very strong strategic option for us as we go forward. The issues, the downsides that we talked about, and again, you know, there is a fairly high fixed cost. We talked of the 625 people, whether you're producing any power or not, that, you know, there's salaries that are there. So the economics are what we really need to be looking at and focusing at. I believe that we can complement wind, solar, hydro. There's a lot of different items. We provide a base load source. And again, you know, we're looking at everything that we can from the technology of Cooper itself, looking at doing some potential flexible operations where we'd be able to maneuver around, and when we have real low load on the grid and very high wind penetration, a lot of generation, finding ways to be able to for us to be able to down power and be able to alleviate some of that congestion as we're going forward. So the commitment by, you know, this becomes now a kind of a decision of really of the people, and that's why I appreciated you allowing me this opportunity to be able to go through. You know, every person, if you talk to anybody at Cooper, they say that what their number one job is to protect the public health and safety. So if you peel that back a little bit, who's the public health and safety? Well, that's our family, that's our friends. So obviously, we believe that it is very safe. It has to be respected, and I believe that we have you know, a good combination of an excellent workforce. We've very engaged. When info comes in, they're just amazed at the Nebraska work ethic, how well people are working to make sure and keeping the plant in very good shape. So I see a lot of potential possibilities. We are, as I said, you know, we're looking at following technologies for small modular reactors that would be a lot smaller than ours, and so therefore you wouldn't have as much of a fixed cost. That may be a possibility that we have in the future. Right now, a lot of it depends upon where we go as we go forward. We're currently looking at that from a strategic standpoint, but we have to look in timeframes 10, 20 years out of where we're going to be going. To be quite honest with you, with everything from a carbon standpoint, and as I see where everything is going, it just makes sense to me. But that's the engineer in me, so.
Thank you. And kind of since we did talk about the Fort Calhoun facility, can you explain why it closed, if you know that answer?
Yeah, that's actually owned by OPPD, so I don't have all of the specific details that are in there. But I know that it was something that, you know, the nuclear community is a fairly small community, and so it's something that I know when OPPD did that, they were it was not an easy decision for them. And I will tell you that the day it closed, it hit a lot of people very emotional down here also. You know, it's like losing a brother, you know. So in the end, you know, I believe it was economics, but again, I don't know all the details. It was operating. They had worked through a lot of different issues. They were doing very well. But again, that's, you know, from a strategic direction, that would be, I would have to defer to OPPD for those reasons.
Thank you.
Mm-hmm.
So we do have another question from Martin. He was wanting to know what the residue is that nuclear energy produces.
The residue, did you say?
Yeah.
Okay. Yep. So when we, it's a very good question, Martin. So the fuel bundles, I said we replaced about a third of the core, so roughly 180 fuel bundles. And so those go into underwater. They stay underwater and they stay in our spent fuel pool where they remain cooled until they've decayed off. And then we will take them out and we will put them into what's called a dry storage facility. And in that particular storage facility, they would they sit there, and we monitor them. They're then very, very passive. They're sitting there waiting for the final repository as we go forward. So, but if you look at 50 years of operation and looking at what you have, people sometimes have this vision of large amounts of waste, taking up, football fields of area. That's not the case. These fit onto a fairly small pad, and as I said, everything is passive in that particular one. They've been designed to withstand extreme environmental events. In fact, there were some that were over in Fukushima when the tidal wave came in that went underwater by 50 feet. They're designed to be able to operate under 50 feet of water. They went through and there was no damage at all to them during any of that. That was never a problem at all with the fuel storage. So very robust storage systems that they currently have.
I didn't know that. That's
Yeah,
really cool.
Did that answer your question, Martin?
Martin, if you want to add that in the chat, he does have another one.
Okay.
So is the lead used as a shield for radioactive material? And then how long does a chemical reaction take inside the reactor?
So the lead is a very effective shielding. So yes, we do have lead, and that provides shielding. So does water. So when if you remember that picture where you're looking down, I was talking about it being underwater. We always maintain it about 10 feet underwater, and as long as it's underwater, people can be up on the top and they're not seeing any sort of significant radiation in any sort of fashion. So between the shielding, the concrete, all these things have different amounts of shielding. Lead is by far one of the more effective shielding that we use, and so we'll put that up. And again, throughout the plant, we may have some lead shielding to be able to get us so that we can do the maintenance and do that under lower dose conditions.
Gotcha.
There was a second part to that question. I don't remember what it was.
Yeah. So how long does a chemical reaction take? So how long does fission?
So the fission takes place in literally microseconds. It's actually a nuclear reaction. It's not a chemical reaction. It's not like burning something. So it will, as we have, I didn't go into a lot of the details, but we have control rods that are in between the different fuel bundles, and what those control rods do is those basically stop the neutrons so that you keep those neutrons from going into the core. So we can basically shut down the core from 100% power down to something less than 5% power in less than 5 seconds. So it very rapidly will drop it on down. As you're going out there, again, this reaction is something that occurs, and it's occurring in the microsecond type time frame when you're looking at each individual fission. To start the plant, though, when we start up coming up out of an outage, it takes us about 24 hours to get to the point where we are producing enough energy. We start pulling rods and start going through there. It's about 24 hours before we have enough energy where we can actually start the turbine up and actually generate. And then we will spend probably about another 4 or 5 days getting ourselves up to 100% power. So again, fairly slow, methodical process. And again, we're doing that for purposes of safety, to make sure we're maintaining all the margins. They're checking constantly, making sure that they're getting the right results, what they expected, and again, working their way through using all their detailed procedures and all the oversight.
And Martin just put it in the chat. I'm sure you can see it, but
Yep.
You did answer his question.
Okay, thank you, Martin.
And then, is there ever any worry about leakage into the river?
So yeah, so all of the systems that we currently have always make sure that that we have not only for the condenser, I talked about the condenser, and I said that the condenser is actually at negative pressure. So the steam that's in there that's potentially, and has contamination and everything in there, it's at a much lower pressure, and we're pumping water through those at a much higher pressure. And so if there's a leak or something, they go from the condense or from the from the river, it goes into the condenser, so it never leaks its way out. Same thing occurs on other safety systems. We always make sure that we have higher pressure on all the systems that pump out of the river, and then we go to an intermediate system, and so any sort of leakage will always go into the plant. The same thing occurs on the reactor building. The reactor building is always at negative pressure. So if you have any sort of leakage, it's going to come into the plant instead of going out from the plant. We monitor, have extreme amounts of monitoring that we watch, and we detect and monitor for any sort of signs of any sort of radiation. But again, all of it is contained and doesn't leak out, it leaks inward.
Gotcha. Thank you.
Mm-hmm.
And then, so you said it's up to sorry.
It's okay.
So your paperwork is up until 2030, and then you said it can go up to 2050. Do you think it can go past that as well?
There, when we look at the, based on all of our assessments and engineering, looking at it, and EPRI's input to the core, we're doing every outage, we're going inside the core, we're doing all kinds of examinations on various items in there. We don't really see anything, and they're currently looking beyond for the potential to be able to run 100 years. None of the plants, we don't have a lot of operating experience out that far out. So there's other older plants that are going, and we'll continue to be monitoring them. That's some of the research that we stay input with for EPRI, and they provide us a lot of information as we're going forward. That would be something, again, we would end up having to assess, but certainly there is no, we know that from a physical asset, everything is in there. We would be looking at, and during that time frame, we would, excuse me.
We can still see you pretty well.
Okay, sorry. We would, there are certain amounts of things that we would be upgrading, like for example, our low pressure turbines. They would be in there. We'd be looking at replacing those. The whole idea that we've used here is to be able to, as the asset ages, we've been upgrading as we've been going to make sure that it's always able to run. And again, it provides very good equipment reliability, and then also it allows you to be able to continue going forward. We don't see anything stopping us at this particular time frame. We have not done the complete study for license renewal. It's a very extensive. It takes us about 3-4 years of looking at it, at all different studies of making sure that we're able to do it. Then we provide the application to the NRC, and they review that, and they go through a lot of different details and inspections and make sure that we've done our jobs appropriately. And then they would grant it for another 20 years and going out to 2054. There is a lot of optimism within EPRI that they believe that they'll be able to continue operating beyond that. But again, some of that testing is just now beginning, because some of the plants have just recently entered. There's probably a handful of them that have started entering into the beyond 60-year life. So that's there's, again, they'll be gathering experience. We share all the time information back and forth between the various different units. It's part of what we do to make sure that we know that there's safety. So if there's an issue, or if another plant finds something that they hadn't expected, we will be going in during the outage and be doing inspections on those items that outage. So again, it's a very very tight-knit, close community, to making sure that we've got everything, and we know and we understand any sort of degradation mechanisms, and so they're all being monitored and being detected.
Okay. if the license was, like, if you weren't able to renew your license, how does the plant close? What would happen there?
So in the event that we decide not to extend the license in 2034, we would in January basically shut down the plant just like we normally would for a refueling outage. We would remove all the fuel out of the core and put it into the spent fuel pool. We would submit in a letter to the NRC that would basically describe that we are ceasing permanent operations. And then during that time frame, what we would do is we would be putting things in place, getting ready to move all the fuel as it over a 3-year time period, letting the fuel decay enough that you're able to put it out onto the dry fuel storage pad. Once you get it out to the dry fuel storage pad, then what we do is we would begin the demolition of the plant. And we have a decommissioning trust fund. It's required by law for all nuclear plants. Ours is fully funded, and we would start the demolition to go in and demolish the plant, bring it on down to basically bring it back to a brownfield configuration.
Okay. Another question from Martin. Can the plant use uranium-238 and uranium-235?
Yes, the majority we have. So the uranium-235, most of the fuel that's in the core when it comes in is uranium-238. We have a certain amount of enrichment that we would go through of, it exists in both isotopes. And so what we do is we enrich a little bit more of the uranium-235. Then over time, what happens is we're able to use that uranium-235, and it's able to be, as the nuclear reactions go, we're able to use that, and that's how we're able to manage that. So I talked about every 2 years we do the refueling cycle where we take about a third of the core out. What we do is we shuffle the rest of those around. So just like you would on a campfire, if you have a campfire, closest to the core is where everything's the hottest, right? And outside the wood isn't burning as much. So when you have a campfire, you put your new wood on the outside, it starts burning. As it burns on down, it starts going more towards the center, and you put other new fuel around the outside. It's that same sort of concept. So as it burns, we're continuing to put it in closer and closer to the center of the core, so it is able to burn, and we're able to use the uranium-238 as it goes through there. So both of them are used. The majority of the fuel that's in there is actually 238. The one slide that I showed you talked about 235 because that's the fissionable part. There are a variety of other ways that we can end up using and converting that uranium-238 to something that we can actually end up using it and making fission with.
Thank you.
Mm-hmm.
All right. So, since it looks like we're running low on questions, if anybody has any last minute questions, please put that in the Q&A chat. We'll probably give it just a minute or two left if there aren't any other questions, and then we'll end it for the night. I just want to say thank you, Dan, again, so much for speaking tonight. This is awesome.
Well, thank you for asking. It's there's it is a unique and it is a different energy source, but it holds an awful lot of promise. And when you look at some of the dynamics that we're currently facing, and some of the items, I believe that the carbon free is it's very important. And I think that there's ways for us to be able to do, and that's exactly what we're doing, is we're looking at what's the best ways to be able to maintain. And again, it's all about maintaining reliable as well as affordable and dependable energy and carbon free. So we're trying to hit and work on hitting that sweet spot. So again, it becomes a very big factor to be able to produce reduce our overall carbon output. And that's very important to NPPD and to the people of Nebraska.
We'll give just one more minute.
Okay. I got to figure out why my timer lights went out. So
I'm surprised the ones on the other side didn't go out.
well, those are actually inside my office here. I think the other ones were actually outside. So
Okay, that does make sense though. All right, Dan, I think we're good for tonight. So thank you again. And thank you all for joining tonight. It was really great. So have a good rest of your Tuesday evening.
thank you very much. Thank you, Laura. And thank you to all who looked. I hope it was valuable to you. And if you have any questions, do not hesitate on reaching out. So thank you.